Morning, everyone. I'm Sugan, final year integrated PhD student. I work in the area of turbulence with Professor Samriddhi. And today I'm going to talk about an ongoing work uh, about the effect of spatial dimension on the dynamo effect using a particular closure model called the EDQNM. So this is work in collaboration with Professor Dario, Giorgio, and my advisor. So I'll split it into three parts. First, I'll explain the EDQNM closure model briefly, and then what aspect of dynamo effect that we are looking in, which is the effect of spatial dimension, and finally the results from our preliminary results from our model. So starting with the EDQNM closure model. So closure problem occurs whenever we have a couple statistical moments for systems when it has more number of unknowns. For example, if we have a second moment which depends on third moment and third moment which depends on fourth moment and so on. So typically this happens because of the nonlinearity in the system. For example, in the Navier-Stokes turbulence, the nonlinearity introduces the closure problem in the system. And one way to overcome the closure problem is to hypothesis as hypothesis and close the equation at some certain level. For example, for the Navier-Stokes turbulence, this eddy viscosity is one famous closure technique which is used, but there are a lot of other closure hypothesis models which are used in the turbulence community. So some of them are stochastically modeling the system, some are statistically reparametrizing the system. So the EDQNM approach, the EDQNM model is basically a two-point closure model done in spectral space. And I'll briefly explain the term, and then we'll move on to apply this closure in the MHT part. So the basic rough idea is that to assume turbulence is close to Gaussian, and we all know that it is indeed not Gaussian. It has strict deviations from Gaussianity, but we sort of assume that at the fourth order moment is Gaussian, which means the cumulant would vanish, and we can decompose the fourth moment in terms of the second order moments. But the third order moment, we don't make any assumptions in this model, which otherwise it will become linear system. So we keep the third moment evolve on its own, but the fourth moment we assume it to be Gaussian. So that's why the name quasi-normal. It's normal, but it's not completely normal. That's quasi. Next is if we take the quasi-normal model, and it has its own problems because of the oversimplification that we done in the normal assumption. So to overcompensate that, we need to introduce a saturation term for the third order moment by introducing an additional time scales for that. So we call those time scales as eddy damping, and that's eddy and damp. And finally, for realizing such models in physical reality, one needs to introduce a Markovian assumption, which assumes a short memory of the system for the third order moments. So that's sort of like saying if we invert this third order moment, we have a operator with an exponential, and we say that the time scale at which this third order moment changes is fairly small, and then we approximate with this model, with this approximation. So that gives rise to the eddy damped quasi-normal Markovian model, and this is a famous closure model applied for the turbulence picture. It follows the Kolmogorov phenomenology of cascades, but it does not give you any intermittent effects or any deviation from Gaussian. No intermittent effects are observed. So, but it has its own advantages and merits because it is a one-dimensional model. It is computationally cheap, and one can reach a really high Reynolds number using this EDQNM model. And here, merely the dimension acts as a parameter when we do all the simplifications, and which would allows us to change the dimension to even to non-integer values, and it indeed preserves what we observe in real life phenomena. For example, the inverse cascade in 2 dimensions when you put d equal to. So this is the EDQNM spectrum, which I have done for various dimensions and with compensated with k to the power minus 5/3, showing a constant at 1. Now this is the model for the turbulence. Now if you go to the MHD equations, one still has a closure problem because this still has non-linearity and it has a coupled equation, and we do the similar EDQNM approach with some minor extra assumptions that there are no cross correlations, and we need to add an alpha and time scales into the eddy damping terms and so on. And that finally gives rise to the EDQNM MHD closure model, which has its own uses that one can range over a wide range of Prandtl number or in the landscape of magnetic and as well as kinetic Reynolds number, and we can investigate the cascades, helicity, the decay of the system, and we are interested in this particular problem, which is the dynamo effect. So, for example, equation 10 and 11 roughly outlines how does the model look like, the energy spectrum of kinetic and magnetic field, and they have the transfer terms. One is self terms, which interacts within the system, and the I stands for the interaction terms, which communicates between the kinetic and the magnetic part. Now, the second part is the dynamo problem, which is in fundamental physics perspective, it's just amplification and sustainment of magnetic field in electrically connecting fluids and electric fluid flows and plasmas. So the problem is vast and complex, and it happens in a wide range of magnetic and kinetic Reynolds number, and we are particularly interested in the effect of dimensions in the dynamo problem. So in what dimensions does the dynamo affect, and what are the dimensions in which no dynamo crossover happens, if so. So the anti-dynamo theorems, which is known for a long time, is one concrete result which says that strictly for D equal to two-dimensional flows or axisymmetric flows, for them a dynamo effect is strictly not possible. One can prove it rigorously for the 2 dimensions, but for other dimensions, including non-integer dimensions, one has to reduce a model to look into it. So one particular model which succeeded is this Krejcik-Kazantsev model, which successfully predicted the analytical properties for a small scale dynamo growth. That model particularly assumes that the velocity field is Gaussian in time with a spatial correlation of this form, with a Gaussian in time, but with a sort of with a particular spatial correlation. So with that assumption, one can look at the magnetic correlation for the same time, this H of R, and the Kazantsev model, this assumption simply reduces to this particular equation, assuming, of course, isotropic and homogenic conditions, so that the L and L stands for the normal and transverse correlations. And this equation, via this simple transformation, the Kazantsev model shows reduces it to a nice Schrodinger equation with this transformation, and the V of R dictates a potential, and the model states that for a dynamo to be possible, you need to have bound states within this potential. And if you assume this correlation to have a power law, spatial power law with a exponent xi, then one can look at V of R in terms of xi, and can get a critical exponent xi critical, which is root of 11/3 minus 1, and that sort of dictates a critical exponent for which the dynamo will be possible. And this model, as I said, one can extend it to accommodate various spatial dimensions in the flow, and one can also include compressibility effects in this model. And this is an interesting result that was shown in 2019, and this shows the range of critical exponent for which the dynamo would be possible, and which is, for us to say, for 3, the critical exponent has to be greater than 1. And as we increase higher, as we move away from 3 in either directions, we see that the critical thing has to be is actually larger than 1. That means the flow has to be more smooth for dimensions other than 3 for a dynamo to take place. Yeah, and the dotted lines are when we involve compressibility. So when we allow the compressibility to exist, then the critical exponent for a particular dimension hits a smaller value. I mean, even without even not going very smooth, one can get a dynamo in other dimensions than 3. So yeah, 3 is like a convex point at the bottom, and of course at a 2 you can never have a dynamo. That's because of the anti-dynamo theorems. Okay. Okay. Now moving into the results that we do from our EDQNM MHD model. So as I said, this is it's not a purely analytical model. Rather, it's not a fully DNS model. Rather, it's somewhere in between. We try to look at the same picture to see in what dimensions does the dynamo exist. So as you can see, I take a EDQNM spectrum and then introduce a small magnetic energy, see a tiny magnetic energy into it, and look at the growth of the magnetic energy. So for dimensions 3, 4.5, 6, and even for 2.1, we see a dynamo to exist. So, but at d equal to 2, we don't expect the dynamo to exist. You see a growth of magnetic energy, and then it decays as time progresses, and that no dynamo effect persists even for dimensions close to 2. This is in conjunction with the fact that the inverse cascade in the EDQNM model persists for up to a critical dimension, which is around 2.03, stated in papers by Frisch and others. Similarly, on the other hand, as we go to higher dimensions, you see the dynamo effect again fades away. And then to summarize, you see that across several dimensions, the red denotes a strong saturation of the magnetic energy, and the blue denotes that the magnetic energy dies away. So as we go across the dimensions, for d close to 3, the dynamo seems to be stable, and for as we move away from 3, the dynamo does not stay in our model. So the reason here can be understood by looking at the transfer term, which is responsible for the growth of the energy magnetic energy spectrum. As you can see, the blue and the green, which is for the d close to 2 and for higher dimensions, they have a negative transfer, which is sort of removing energy away from the spectrum, whereas the dynamo, the dimensions where the dynamo is existing, they have a positive transfer spectrum, and we can understand why that sort of happens for d equal to 2. As I said, it's because of the persistence of inverse cascade, and for higher dimensions, it's a different reason that the cascade is that there is some sort of bottleneck effect. There is a stronger cascade towards lower wave numbers. So even with the interaction, the energy is dissipating away, magnetic energy is dissipated away by the resistive scales. And so I'll stop at it, but the future work, this model is robust, and one can study the compressibility effects, and I can introduce the helicity into the problem and see how does these two parameters affect the resistance of dynamo across different dimensions. And yeah, I'll be happy to take questions.
So, any questions?
You've shown some consistency checks, right, with other results in 2 dimensions and so on.
Yes.
So there are some results in MHD turbulence based on interaction of alpha and waves and so on. I'm sure you must be familiar with those.
Yes.
But does your approach have anything to say on that problem? Or is it a different problem completely?
This is a completely spectral picture.
Hmm.
So I don't, I currently, I can't comment on,
Because you have used the word isotropic.
yes.
Whereas, if I remember right, that work assumes an overall large-scale magnetic field and then looks at interaction of alpha waves against that. Okay, we can talk later.
Yeah, sure.
Maybe a different problem.
So any more questions? So if not, we can thank the speaker.